In this video, we will see how to build quadratic function models. To begin, let's see what is a mathematical model. A mathematical model is a mathematical description of a real-world situation. That means that now we are going to have equations that represents something in the real life. Here we have the general form of the quadratic function. The quadratic function has a power of 2, and it can have up to 3 terms. The first term is the quadratic term, the second term is the linear term, and the third term is the constant term. A, B, and C can be any real number, but A cannot be 0 because the quadratic function must have the quadratic term. If A is 0, then you wouldn't have the quadratic term and it wouldn't be a quadratic function. The graph of the quadratic term is a parabola. If A is a positive number, the parabola would be opening upward. And if A is a negative number, the parabola will be opening downward, like the example we have on the screen. If you can tell, here it says that A is less than 0. That means that this graph corresponds to a quadratic function where A is a negative number. That's why it opens downward. Now, H and K represent the coordinates of the vertex. In the case of a parabola that opens downward, like this one, the vertex corresponds to the highest point of the parabola. But if the parabola would be opening upward, like this, the vertex would correspond to the lowest point of the parabola. There are many situations in real life that behave in parabolic curves. Let's see a very important example. The parabolic motion or projectile motion. This is the most common application of quadratic functions. You have probably already seen this in your physics class. Every time that you throw something up in the air, the path that follows is a parabolic trajectory. It forms a parabola. This happens with any object. Here on the screen, you can see 5 different examples of projectiles. The projectile is the object that you throw. And if you can tell, all of them follow parabolic trajectories. Now, since the trajectory of all of the objects that you throw in the air are parabolas, that means that you can represent them with quadratic functions. And then you can use that quadratic function to make different calculations. For example, you can calculate the time it takes for the object to fall down, or you can also calculate the maximum height the object reaches, or the time it takes for the object to reach its maximum height. Now let's see how we can build the mathematical model of a projectile that's being thrown into the air. Here we have again the general form of the quadratic function. Now let's see the parabolic motion model. If you compare them, you can tell that both functions are pretty much the same. The only difference is the letters, the symbols that it's using. That's because each letter is now representing a specific value. Let's see what each letter represents. H means height and T means time. So H of T means the height at a particular time. That means that we can use this function to calculate the height of the object after a certain amount of time after it was thrown into the air. T represents time, usually in seconds. G, which is the coefficient of the quadratic term, means gravity. If the distances in the problem are being measured in feet, the value of G is going to be minus 16. And if the distances in the problem are being measured in meters, then G is going to be minus 4.9. Now, VI represents the initial velocity, and HI means the initial height. If the object was thrown upward from the ground, that means that its initial height was 0. Therefore, the third term would be 0. So you wouldn't have a third term. In that case, your quadratic function would only have the first and second terms. Let's now see how to build the model of a word problem that involves a parabolic motion. This first example says, a ball is thrown upwards from the top of a 40 feet high building at a speed of 80 feet per second. Then we have 4 different things that we need to answer. First, letter A. Write the model of the ball's height above ground. Okay, on the top right of the screen, here, I already wrote the general model of the parabolic motion. So we are going to write it with the values of this problem. First, we already know that the initial height is 40 feet because that's the height of the building. 40 feet. Okay, and the problem also tells us that the initial velocity is 80 feet per second. And since the distance units are in feet, that means that g is going to be 16. So with that information, we can build the model. The function is the function of height in a specific time equals minus g, which is minus 16t squared, plus the initial velocity times t, which is 80t, plus the initial height, which is 40. Okay. So this is the model of the trajectory of the ball that was thrown from the top of the building. Let's answer the next letter. Okay, B says, what is the maximum height of the ball? Okay, if we see the trajectory of the ball, the maximum height will be reached exactly at the vertex. And we know that the vertex is coordinate h, comma, k, where h represents the x coordinate of the vertex and k represents the y coordinate of the vertex. It's very important that you don't confuse that h with the h of the function, because the h of the function means height. And the h of the vertex is the x coordinate of the vertex. And the x-axis, or the x value, is not height, it's time. Okay, so those are different h's. Okay, so in order to find the maximum height of the ball, we are interested in the height. That means that we want to know what is this height, which is a value of y. So we want to know the y coordinate of the vertex. We need to know the value of k. Now, there are different ways that we can find the coordinates of the vertex. One way would be to transform the equation to its vertex form in order to identify the vertex. But another way to do it is using 2 formulas, which I'm going to show you. The formula to find k, which is the y coordinate of the vertex, is 4ac minus b squared over 4a. A, B, and C are the coefficients of the model. So A, B, and C. A is the quadratic term, well, the coefficient of the quadratic term. B is the coefficient of the linear term, and C is the constant term. So K equals 4 times A. A is minus 16, times C, which is 40, minus the square of B, which is 80, over 4 times A. minus 16. So K equals, okay, 4 times minus 16 times 40 is minus 2,560 minus the square of 80, that's 6,400, over 4 times minus 16 is minus 64. That equals minus 2,560 minus 6,400 gives us minus 8,960 over minus 64. And dividing negative 8,960 over minus 64, we get 140. So K is 140. K is the y coordinate of V, of the vertex. And we know that heights, and we know that the distances are being measured in feet. That means that the maximum height of the ball is 140 feet. Okay, now let's solve question C. It says, after how many seconds will the ball reach its maximum height? Okay, so we already calculated the maximum height of the ball, which was the variable k. And now it says after how many seconds will the ball reach its maximum height? So we are interested in knowing time. So we know that here is where the ball reaches its maximum height, but we want to know how much time it takes from when the ball was thrown to where it reaches its maximum height. We want to know this amount of time. That is given by the x coordinate of the vertex, which is h. So now we want to know the value of h, the x coordinate of the vertex. You already know the formula to calculate k. Now the formula to calculate h is h equals minus b over 2a. Let's use it now to find h. H equals minus b, b is 80, over 2 times a is minus 60. So h equals minus 80 over 2 times minus 16 is minus 32. And minus 80 over minus 32 is 2.5. Okay, so the question was, after how many seconds? We know that we just found h, which is the x coordinate of the vertex that represents time. So 2.5 represents time in seconds. So the ball will reach its maximum height after 2.5 seconds. Now let's solve the last question, D. Okay, so I kept on the right side of the board the answers of the first 3 questions and the formulas to calculate the coordinates of the vertex, h and k. Okay, but now we are going to answer the last question, letter D. Letter D says, when does the ball hit the ground? Okay, and it's missing a question mark here. Okay, when does the ball hit the ground? Okay, we know that the ball hits the ground at the end of the parabola. And since it's ground level, we know that the height here is 0. Okay, that's important because remember that the function gives us the height after a certain amount of time. The question says, when does the ball hit the ground? We're looking for time. after how much time after being thrown does the ball hit the ground? So we want to know the time it takes from the start to when it hits the ground. So we're looking for what will usually be the x coordinate, but now it's t. Remember that t represents time. So the height, we know that it's going to be 0 because it's in the ground. Let me write the function. Minus 16t squared plus 80t plus 40. We want to know the value of t when h is 0. When the height is 0, how much time has it passed? So we have a quadratic equation equalized to 0. There are different ways that we can answer this. One way would be trying to factor it and using zero product rule. But remember that there is a general way to answer quadratic equations. The general formula. The general formula says that x equals minus b plus minus the square root of b squared minus 4ac, all of it over 2a. Now let's apply it to this quadratic model. Remember that a is minus 16, b is 80, and c is 40. So x equals minus 80 plus minus the square root of b, 80, squared, minus 4 times a, minus 16, times c, 40, all of this over 2 times a, minus 16. Okay, so x equals minus 80 plus minus the square root of 80 squared is 6,400 minus 4 times minus 16 times 40 is 2,560. All of this over 2 times minus 16 gives us a minus 32. X equals minus 80 plus minus square root of 6,400 plus 2,560 gives us an answer of 8,960 over minus 32. Okay. X equals minus 80 plus minus the square root of 8,960 is 94.66 over minus 32. Okay, here is where we divide into answers. First adding and then subtracting. X1 equals minus 80 plus 94.66 over minus 32. This gives us an answer of minus 0.46. Now let's answer x2, minus 80, now minus 94.66 over minus 32. And this gives us an answer of 5.46. Now, which one of both answers is the correct answer? Okay, so the question is asking us for time. One answer is positive and the other one is negative. We can't have a negative time, so the positive answer is the correct one, 5.46. That means that the ball hits the ground after 5.46 seconds. Okay, so and now we answered all of the questions of this problem by using the quadratic model that we built. Now let's answer a shorter example. Example 2. It says, a boy threw a rock upward from the ledge of a 30-meter high cliff at an initial velocity of 48 meters per second and landed on the sea. The model of the rock's height above sea level is modeled by the function h of t equals minus 4.9 t squared plus 48 t minus 30. Find the maximal height of the rock. There, okay. So the question is to find the maximum height of the rock. Notice that in this problem, the coefficient of the quadratic term is minus 4.9. That's because the problem is measuring distances in meters. Now, we don't have to build the model because the problem already gives us the model. It says that ht equals minus 4.9 t squared plus 48t minus 30. And it says find the maximum height. Remember, the maximum height corresponds to the vertex, which has coordinates h, comma k. Which variable gives us the height, the h or the k? Remember, the height means that we are looking for the y-axis coordinate, and the k gives us the y-coordinate of the vertex. So we are interested in knowing the value of k. Okay, let's now substitute our values. K equals 4 times a minus 4.9 times c minus 30 minus the square of b, 48, over 4 times a minus 4.9. Now let's solve. 4 times minus 4.9 times minus 30 is 588 minus the square of 48 is 2,304 over 4 times minus 4.9 minus 19.6. Now we subtract 588 minus 2,304. That is minus 1,716 over minus 19.6. And that gives us a result of 87.55. Okay, and we're looking for a height, and the problem is measuring in meters. So this is 87.55 meters. That's the maximum height reached by the rock. This third example doesn't have anything to do with projectile motion. It's a completely different problem, but it involves a quadratic model. It says, the fish population in a certain part of the ocean as a function of the water's temperature in degrees Celsius is modeled by the function p of t equals minus 2t squared plus 40t minus 72. Which temperatures will result in no fish? Okay, so let's understand the problem. It's telling us that this model that we have gives us the amount of fish population depending on the temperature of the water. And it's telling us to calculate the temperature that results in no fish. That means when the population is 0. That means that we're looking for the value of T that represents temperature. We're looking for the temperature that makes the population 0. So let's substitute this value in the model. Population 0 equals minus 2t squared plus 40t minus 72. Okay, that means that we need to solve this quadratic equation. What do we do to answer? We use the general equation. We substitute the values. X equals minus b, which is minus 40, plus minus the square root of b, 40, squared minus 4 times a minus 2 times c minus 72. All of that over 2 times a, which is minus 2. Now we solve, minus 40 plus minus square root of, the square of 40 is 1,600. And minus 4 times minus 2 times minus 72 gives us minus 576 over 2 times minus 2 is minus 4. Minus 40 plus minus the square root of 1,600 minus 576 gives us 1,024 over minus 4. And then we divide into first adding plus the square root of 1,024 is 32 over minus 4. And in our second option is minus 40 minus 32 over minus 4. Minus 40 plus 32 over minus 4, that gives us 2. And minus 40 minus 32 over minus 4 gives us 18. That means that we have two different temperatures that make the fish population disappear or become 0. The temperatures (2°C) and 18 degrees Celsius. Okay, so now you know how to build quadratic models and how to use them to calculate different things. Thank you for watching this video.